In a previous video, we looked at how the acceleration due to gravity will affect the motion of an object in one dimension. And the next logical step is to look at motion in two dimensions. So the first thing of note is that g, which is equal to 9.81 meters per second squared, points towards the center of the Earth. So because it points downwards, g only affects vertical velocity. So if I have some velocity that is pointing to the right, for example, this is a v, and my gravity is pointing downwards, well, gravity has no effect on this right pointing velocity vector. It's only going to affect velocity vectors that are pointing either up or down. The next thing we need to be sure we understand, up until this point, we haven't been very picky with our vector notation, but we have to remember that v is in fact, velocity is in fact a vector. And what does that mean? Well, if we have motion in two dimensions, we can have a velocity vector that points at some angle. So now this v has x and y components. So for example, v vector would be equal to some scalar quantity vx in the x hat direction plus vy in the y hat direction. And this vx and vy, these could be any number. I'm just choosing these variables to speak generally. But this v vector could be like 2 in the x hat direction plus 1 in the y hat direction. And of course, this would all be in meters per second. But I just want to give a general example with vx and vy. So v is a vector quantity, and just like with position vectors, if you have a vector quantity, for example, if you have a v1 and a v2, well, you can't just add v1 and v2 together. You have to add the individual components together when you're dealing with a vector. So we're going to be looking at how, in the case of this motion in two dimensions, the individual components of a vector are independent of one another. And the way that acceleration treats these two components are completely independent. So since g only affects the vertical component, g will not affect this horizontal component at all. So when you throw a ball, for example, you're standing, you have a baseball, and you're getting ready to throw it, and say you throw it upwards at some 45-degree angle, well, then it's going to have some initial velocity. And we know that gravity points straight down towards the center of the Earth. And this means that gravity is not going to affect how this ball moves horizontally. So you can break up the velocity vector into independent components, and you would see that over time the ball travels horizontally the same over every instance of time. Now, the vertical travel is going to look very similar to motion in one dimension that we learned about in a previous video, and it's going to move up and slow down and eventually hit v equals 0, and then it's going to move straight down, accelerating towards the Earth. These two velocity components, vx and vy, do not affect one another. They're completely independent. You could do two separate graphs, just like we did two separate dot diagrams, and they would have their own behavior. But how do we show this on a single graph? Well, it's going to be a similar shape to the position versus time graph, which we had earlier. But now we're looking at the horizontal position x and the vertical position y on the same graph. So it's going to literally look like the path of the ball. So this is the literal path of the ball. Why? Because any point along this graph would be the coordinates where you could find the ball. So if I choose a position right here, this is going to have some XY value that's going to tell me the position of the ball. So this has the special name of projectile motion. And when we say projectile, some people think, well, that's a bullet, that has nothing to do with other objects. But projectile just means something that's moving through the air, and it's going to always have this shape. What does that look like then if the object's moving very fast? So you have then like a rifle or you have a cannon, and if you fire the cannon, it's going to be moving very fast horizontally, but it's still going to have the parabolic shape. And if the cannon were perfectly flat and just shooting horizontally, then it would be half of a parabola. It would be perfectly straight, but then tend downwards. And so it would have a downward arc. Okay, so we've said that the velocity at any point on this graph has two components. It has a vertical and a horizontal component. And like I said, the horizontal component is the simplest because since there's no acceleration in the horizontal direction, G points straight down, so that has no effect on the horizontal position. Well, then we know that at every point in time that V is going to be the same horizontally. It does not change. V is going to be the same horizontally throughout the entire path of this object. It doesn't change. And then what happens to the vertical component of velocity? Well, we know that it is changing because gravity is working on it. And gravity is an acceleration. Acceleration is the change in velocity over the change in time. So we're going to first have some large velocity pointing straight up. And just like with this diagram over here, when we considered the one-dimensional case, now we just apply this to this two-dimensional graph. It's the same behavior as the one-dimensional case. So we start with some large initial velocity, and over time, it's going to shorten. Why? Because gravity is pulling it downward, and the acceleration is downward. And eventually we're going to hit some point here where Vy equals 0. Just like in this case over here, it's going to get slower and slower and slower in the vertical direction, and it's eventually going to hit 0 because it has to turn around. It has to go in the opposite direction. And then Vy starts pointing downwards. And over time, it's going to get faster and faster and faster in the vertical direction because gravity is accelerating it downwards. So, to recap, the horizontal velocity is the same throughout the entire path of the object. It doesn't matter if it's a basketball, it doesn't matter if it's a cannonball, it doesn't matter if it's a golf ball. Anything moving through the air has the same initial horizontal velocity as it does in the beginning and the end. However, the vertical velocity is being acted upon by gravity. So gravity is accelerating it downwards at every point along its path. It starts with some large initial velocity, and it goes downwards and decreases until it's at some large final velocity that is negative. When you look at the graphs of position versus time, velocity versus time, and acceleration versus time for this two-dimensional trajectory, you're going to see different behavior because the velocities are independent of one another. So what that looks like is if I consider just the position in the horizontal direction. So horizontal. Well, what happens to the horizontal position over time? It's increasing. If you throw a ball, it's just going to keep moving further away from you horizontally. I'm not talking about the vertical component now. I'm talking about x versus time. The position of the ball will just increase. Well, what is the slope of this line? What is the velocity at all times for the trajectory in the horizontal direction? Well, we said previously that it's constant, so you'll have some constant velocity. This is now velocity versus time. Again, that's this horizontal piece right here. This horizontal piece tells us that the velocity is constant in the horizontal direction. So what is the slope of this flat line right here? So the slope, now this is acceleration versus time, is 0. So I draw a straight line at a equals 0. That's just the horizontal component. The position is increasing uniformly with a constant slope. The slope is constant, so I have some constant value here for v. And I know the slope of a straight line is 0, so my acceleration is 0. Now I have to look at the vertical component separately. So for the vertical component, previously, now we can consider what the graph looked like in the previous case because it's going to look exactly the same. The position versus time, again, this is time now. It's going to look the same, but this is considering the one-dimensional motion. We're only looking at the vertical position. So this is literally the graph of this one-dimensional movement over here of the ball. Well, what does the velocity look like? It's going to be the same as the one-dimensional case. So now this is velocity versus time for the vertical case. And it's going to be a steadily decreasing straight line. So this is time, and now velocity starts positive, it gets to 0 at the top of the parabola, and then it gets negative. So the acceleration then is going to be the acceleration that we've learned about now. It's just g, and it's actually going to be a negative number. So g down here is 9.81. This is g, and g is going to be a flat line. So to recap everything, gravity only works in the vertical direction. So it will only affect the vertical component of velocity. We have to treat the x and y components of velocity independently because it's a vector. So if we're dealing with vectors, we treat the x component independent of the y component. What that means is that the motion in the x component is completely independent of the motion in the y direction. We have to treat them independently. That means they have different behaviors on their graphs. And we're going to be looking at this much more. It's pretty complicated, but we're going to be working problems and seeing how we treat the components of velocity independent from one another and what that means for solving motion problems.